What is a quantum computer? In order to get a good perspective on a future quantum computer, let's first have a look at the classical computer.
Let's have a look at the theory.
An essential part of a classical computer is the integrated circuit. The integrated circuit is an amazing piece of engineering. On integrated circuits, you can find nowadays billions of transistors. And these transistors, in turn, are used to construct classical bits. These bits can represent either a 0 or a 1. And we use these numbers to perform calculations with a computer. We find integrated circuits virtually everywhere, and they completely changed our daily lives. Nonetheless, while the modern supercomputer is much faster and much more accurate than the abacus that was invented thousands of years ago, they are bounded by the same physical principles. This century, we have the opportunity to develop something radically new and use quantum mechanics to build quantum computers.
How can quantum solve this?
Quantum mechanics can offer unique phenomena. These include superposition, interference, and entanglement. Let's start with superposition. Whereas a classical bit can only represent a 0 or a 1, its quantum mechanical counterpart, the quantum bit or qubit, can take on both values at the same time. It's not that we just don't know what the value of this qubit is. The qubit can truly be in a superposition of two states and represent both 0 and 1 at the same time. In a classical world, if we throw a ball to a plate with two slits, the ball will go through either the left slit or the right slit. In a quantum mechanical world, instead, a quantum particle can do something completely bizarre. It can go through both slits at the same time. We can observe this by putting another screen behind it and measure the probability that the ball reaches a certain location. The ball going through both the left and the right slit can interfere. This is similar to the traveling waves in water, but here the ball can interfere with itself. As a consequence, at some positions at the screen, interference is such that the chance to find the ball increases, whereas at other positions it decreases. When we go from 1 to 2 quantum particles, more spectacular effects start to occur. Two quantum mechanical particles can interact with each other and create an entangled state. This means that they share some common properties. For example, the total outcome could be 1, meaning that if you would measure one particle to be 0, then the other particle would be 1. Or, if you measure the particle to be 1, then the other particle would be 0. It are these concepts of superposition, interference, and entanglement that are behind the real power of quantum computing. However, in order to go beyond these concepts, we need to make use of it and create quantum particles that we can control very well for the construction of a quantum computer. The first building block is the qubit, the quantum mechanical particle. The challenge is to find the suitable platform for these qubits and have all the electronics to perform operations with these qubits. Making good qubits is hard. Quantum mechanical effects are usually associated with small energy scales. And in order to see them, we have to work at very low temperatures. And therefore, we build these qubit systems in special fridges. Not just the one that you use to cool your milk and butter, but fridges that can go down to almost 0 Kelvin, just slightly above the absolute minimum temperature. Nonetheless, even at these very low temperatures, qubits are not perfect, and errors can occur. Overcoming this is a big challenge, but highly important. Classical computers can rely on error correction techniques. But for quantum computers, this is not so trivial, as we cannot just simply copy a qubit many times. Quantum cloning is not possible. The theoretical invention that quantum error correction is possible came therefore as a huge surprise. This means that we don't need to construct perfect qubits. And what we can do is combining many physical qubits to construct one really good qubit, a logical qubit. Now, we don't need many logical qubits to build a powerful quantum computer, since many quantum algorithms provide an exponential speedup as compared to their classical counterpart.
What are the caveats?
What we do need is many physical qubits to construct logical qubits. And so, a quantum computer may contain millions of qubits. What are the requirements to advance a system with a few qubits toward a quantum computer containing millions of qubits? In 2000, David DiVincenzo listed 5 key criteria. First, a quantum computer must be scalable. Second, it must be possible to initialize the qubits. Third, good qubits are needed. They need to have a long quantum coherence to make sure that the quantum state is not lost. It is furthermore required to have what is called a universal set of quantum gates, meaning that one can do the operations needed to execute a quantum algorithm. And finally, we need to be able to measure all of those qubits.